Hey all, this is Chris. I'm a software engineer at Wolfram. This project is called the Standalone Applications Project. It's something that we have been working on at Wolfram for a while, and it was recently mentioned in Stephen's 14.1 blog. All right, so for this presentation, my first goal is to just kind of explain what the project is and what we're trying to achieve and how we're trying to achieve it. Then I want to introduce something new. We're trying to roll out a beta program for the project. And then finally, I kind of wanted to give a concrete example of how the development process actually works for a real standalone application. So our goal is to make Wolfram language-based applications practical and appealing. And what I mean by this is we kind of have two applications types in mind. And there's kind of one where we just start from the ground up. Everything's Wolfram language. And that's what we want to give to people, just some completely Wolfram language thing. And we want that to be feasible. And there's another scenario where there's kind of existing software. It's not written in Wolfram. It's written in some other language. It's some, big stack of stuff. And you want to kind of graft on like Wolfram language functionality. So that's kind of another situation that we want to support. And we want both of these situations to be kind of more practical and appealing for developers. And so in order to do that, we've come up with some technical goals. The first of which is the expression API. And we are also calling this the Wolfram Language Runtime. And this kind of allows like a kernel as library role. So instead of kind of interfacing with the kernel as like an interpreter. Like I give you some input, you spit back an output, blah blah blah. What we're doing is the kernel is just kind of like a backend. It's just a library. And specifically, what this means is that you can compile Wolfram language code into executables and libraries. Now, I don't mean compile in the sense of like the compiler project. I mean compile in the sense that you have some Wolfram language code, but you've turned it into some kind of binary that you can run. So next we have the code signing project, the code signing component. Um, and this is kind of a critical thing for actual redistributable applications because otherwise your customers would have to have some kind of relationship with Wolfram. They'd need a license. They'd need a network license server or something. But you probably would prefer it if your customers didn't have to do it and there's some kind of standalone licensing solution. And finally, we've got some pruning strategies. Um, and the reason for this is in order for you to have a standalone application that uses Wolfram, there needs to be a layout, right? There's a whole big set of files that the Wolfram language needs. And the usual layout is like several gigabytes, but that's not really welcome in an application where you're trying to give it to somebody and it doesn't make sense if they would have to download like several gigabytes in order to run it. So we want you to be able to bundle a smaller, more reduced layout. So I kind of wanted to go back to the expression API a little bit. Um, I introduced kind of a concept called kernel dynamic library. So this is kind of a crucial component in terms of the implementation of the Wolfram system. It implements the actual Wolfram programming language and core functionality. And if you want to know where it is, it's in system files or libraries and then your system ID. And so I kind of gave a concrete example here for Windows. So the expression API, right, it basically lives in these dynamic libraries. Um, it's a set of C functions that are exported from that dynamic library. And so they let you do things like build up an expression, evaluate an expression, go from an expression to C types. Another kind of important note is that the kernel runs in your process. It's not like most how, MathLink, it's where for MathLink, there's some separate process and there's two processes communicating with each other. No, it's all the same process. And hopefully another thing that's kind of an advantage for application developers over MathLink is that it's hopefully a little bit less like esoteric. Like, yeah, it's like just a normal C library. It's not some communication protocol. It's just like, oh, there's a function for creating, a complex expression from a real part and an imaginary part. And it's just a simple, kind of easy to understand function. We're hoping it's a little bit more friendly. And like that, that's the point right there. Okay. So, I thought it might be helpful to kind of scroll through and see how the documentation is structured. And unfortunately, we've kind of been rolling out this project in stages. So the documentation isn't publicly available yet. But I wanted to just show this link, and it's in the slides. It just gives you some of the draft form of the documentation. So this isn't real. This is kind of rough, but just in case you wanted to start doing things with the expression API now, here it is. And so I will scroll over to it. So there's, for example, like I was talking about, there's, a function for going from like an integer to add an expression. There's a function for creating a rule from a left-hand side and a right-hand side. There's a function for, say, coming up with a string expression from a C string. And similarly, you can build up the expressions, but you can also go back to C types. So there's something called string data, where you go from the string expression back to the C string, right? So there's kind of building up expressions and then going from expressions down into smaller parts. So you also see things like first and head and that kind of thing. So that's kind of like one category. And then there's another category of functions for kind of like starting the Wolfram session and the kind of details of that. There's functions for the different ways in which you might want to evaluate an expression or a file. So there's kind of several categories of how the expression API is structured. And we're hoping that this kind of gives you some flexibility in terms of how you make your application kind of interface with the Wolfram language. So one final point on the expression API is that developers will be using the Standalone Applications SDK. So this is just a static library that you will be linking against. So as an example of what that would actually look like in a shell command, consider that you're compiling some C file that uses the expression API called application.c. All you have to do is point to the standalone applications SDK directory, and that's this path in the layout. So there's some include files that you need. And then additionally, you have to link to the static library. And that's also in the standalone applications SDK directory. Now to kind of give a more like a high level thing for like if you're using, say, like Visual Studio, as an example of what the settings you might use would look like, you can give it the standalone applications SDK include directory in this kind of configuration menu. And similarly, you can add the static library as a dependency in the configuration. So I just kind of wanted to quickly roll through a simple example of something that uses the expression API in the SDK, and it's just copied from the 14.1 blog. So consider this C source file. It's like a command line program for identifying some string of language that's passed to it. So, you could say the text language hola, and it would say Spanish, that kind of stuff. So the first thing that it does is it starts up the session. Then it tries to kind of compose an evaluation. So it builds up an expression, language identify of some string, and then it kind of tries to break it back down into the name of the language that was returned. So specifically, you can see things like WLR symbol of language identify. And so that's something where we go from a C string to a symbol expression. And there's WLR underscore string of the argument. So we're going from a C string to a string expression. So basically, like I was saying, you're composing an evaluation, doing the evaluation, and then trying to go back to C. And so then again, you can compile it using the SDK, and then you can kind of see how it would actually work. It evaluates language identify of hello there. Language identify returns English as a expression, and then there's some operations that try to get that as a C type, and then it prints it out. Okay, so an additional point, as I mentioned, is code signing. So the mechanism that allows us to have Wolfram language execute even in kind of like scenarios where there's no license is something we're calling code signing. So the kernel, it allows itself to run signed Wolfram language even if there is no license around. So there's kind of three things covered by code signing. There's Wolfram language files. So as an example, there's an expression API function for loading and evaluating a file. If you don't have a license, it's not going to load that file unless the file is signed. Similarly, symbols need to be signed. So there's an expression API function for evaluating an expression. And so it will refuse to do so if there is no license and there's no and there's an unapproved symbol in the expression. Now, a kind of like important thing to note is that there's a set of kind of pre-signed symbols, symbols that are just kind of are useful to have pre-signed for like for matters of convenience. So things like plus or list, that kind of stuff. That we're just pre-signing those. The symbols that are more caring about are stuff that gives away functionality. And then finally, MX files also need to be signed in order for them to be loaded. So what form does code signatures actually take for a developer? Well, it's something that we're calling code signature modules. And these code signature modules can be generated in different ways. But as an example, one is, say, like a web page where you submit your code to us and then you get back a code signature module. And specifically, that code signature module is a C file. And you compile the C file into your application. And once you've done that, the application, the kernel sees what you've signed using the code signature module. So it like understands what you've signed. But an important thing to note here is that, for certain customers, it won't be feasible for you to submit your code to us. So for special cases like that, there's a way for you to self-sign your code and the kernel will recognize it as signed. And there's some other alternatives as well. So for special cases, there's ways where, for example, you don't have to submit your code for us to be signed. All right. So another component that I mentioned was pruning. And as you see, unpruned, it's several gigabytes. It's a few gigabytes. And so this discourages developers from creating applications that use Wolfram language because in order to use Wolfram language, you'd have to bring in gigabytes of layout, and that's a real barrier. So we're trying to reduce how much you have to bring into your application. So one of the major strategies is changing the BLOS backend. So MKL, that's one BLOS backend that we use, is around a gigabyte. But for certain applications, we can change that BLOS backend to a smaller alternative. Fine. Another thing is that we can remove layout components that aren't needed by a particular application. So, right, obviously the Wolfram language, that's a big thing with lots of different sub areas and functionality. But you might have a really specific application that only needs specific functionality. So there's kind of like whole areas of the language that you don't need. And we're hoping that we can remove the components that are necessary for those areas from the layout that you bundle in your application, so you don't have to have as large of a footprint. And so we kind of have two methods for trying to figure out what we can remove. And we'll come back to that later. And so finally, I kind of wanted to give people kind of an idea of what actually takes up a lot of the space in the layout. And this is from, I guess, 13.1. But you see like MKL, that's the class backend, that's pretty large. Auto completion data, Java, um, math, link. There's a lot of stuff in here that your application might not necessarily need all of. All right. So now I kind of wanted to talk about the beta program. So we have a marketing page that we're working on that is not live yet, but it will be soon. And it'll just let you sign up for a form and we'll contact you about the beta program. And I'll scroll through that. And then a kind of a useful example that's in the marketing page is from Area Optics. Area Optics is a optics software company that we've been working on regarding standalone applications. And they basically have all kinds of stuff that's written in the Wolfram language. But for one scenario, they kind of wanted to use that functionality as an add-on or a plugin to kind of like a bigger optics software tool. So this is kind of like the second type of application that I was talking about at the beginning of the presentation, right? You know, you're trying to extend some software with Wolfram language. So what they did was they used the standalone applications project, and they kind of developed this add-on that allows them to kind of use Wolfram language completely under the hood, completely unbeknownst to their users that there's Wolfram language being used, and it's just kind of like an implementation detail. So, you know, users of the optics software tool can just load in their plugin and then do like cool optics stuff. Another example is LSP server. So this is something that we've been working on inside the company. You may be familiar with LSP server. So what it is just we have this extension for Visual Studio Code that allows that implements syntax highlighting and other features for using Wolfram language in an IDE. But unfortunately, the current version of this extension launches a dedicated kernel for it, and this consumes a license process. So we were kind of just thinking to ourselves, well, this is a good example of the standalone applications project. What if we could develop a form of this extension where it doesn't need that separate license process? And specifically, if we use code signing, we don't need the license process. So I was gonna kind of use LSP server as a case study for how development using the standalone applications project works. So first you have to determine what you're using Wolfram language for. So for LSP server, it's pretty simple. You just have to load the packlet and then start the server. And in terms of what that actually looks like in terms of the expression API, there's kind of two components. There's one component where I put the Wolfram language code. So there's LSP server app.tbl, but then there's also a C file, and this is the expression API that's actually responsible for starting the kernel and loading LSP server app.tbl. So you'll see, you know, there's one call that starts up the session, and then there's another call that actually is responsible for loading LSP server app.tbl. This looks kind of complicated, but that's just because it's trying to figure out, you know, like where's the relative path of LSP server app.tbl in relation to like the executable. So it's you know trying to figure out where LSP server app is, but really it's just get of LSP server app.tbl. But an issue that this brings up is there's an argument for WLR underscore start runtime that controls the signing behavior. So, for example, if you give it signed code mode, that forces the kernel to be locked down. That forces the kernel to use code sign. But an alternative is that WLR license or signed code mode allows the kernel to use a license if one is available, and then only if it isn't do we use signed code mode. So this is the option that we prefer for development. So when you're developing things, you want to try different things, and you don't want to be locked down, and you just kind of want to be experimenting, you would use WLR license or signed code mode. But then as soon as you're kind of ready for production, you're deploying your application, that is when you would switch to WLR signed code mode. So as you'll see, this is trying to be like an example of something you might deploy. So we're just using signed code mode. So additionally, something I thought would be interesting to bring up is that there is code signing in terms of the expression API. So WLR eval won't evaluate something if there's an unapproved symbol in the expression argument, but that actually doesn't apply to this scenario because all of these symbols get file name join. They're all signed by default for convenience. So this evaluation goes through because there's no unapproved symbols. However, when you use Git, it does check if the file that you're loading is signed. So for example, lspserver.app.dl, that's what you need to be, that's what needs to be signed. And so that's ties into the next step where you have to get a code signature module for lspserver.app.dl. And so, for example, you might go to a web page and you get the C file, that's the code signature module, and then you just have to compile it into the executable in addition to lspserver.app.c. And once you've done that, your executable will understand that the Wolfram language file is signed. So then you want to bundle the layout so that it's kind of standalone. And that is where something else that is irrelevant from the C file comes into play. So if you look, you'll see that there's this third argument to WLR SDK start kernel called resources layout files. So really what this is telling the kernel dynamic library is that I want you to find the layout files that you need relative to the binary, relative to LSP server app, add resources, layout files. So it's basically saying this is where you can find those layout files that you need. Because it's the standalone applications don't just need like a single thing, they need the whole layout of like resources that go along with the Wolfram language. So when you start up a session, you kind of have to tell it where to find it. And there's different ways you can kind of structure, where those resources are. So you kind of have to tell it, okay, resources layout files is where those files are bundled relative to the standalone application that I'm making. And then finally, you will want to prune the bundled layout. And there's two options for this. The first option is something we call dynamic analysis. So this is something where we just run the application in a special mode, and we try to track what files it accesses. And we're using that as a basis for a guess of, okay, these files aren't accessed, so maybe we can remove them. And so this isn't an automatic process. There is an element of pruning by hand to it. Additionally, we have a tool that just kind of tries to automatically analyze Wolfram language source code and doesn't have to run it. And it just tries to figure out, well, what are the dependencies of this application just from that analysis? And this is still a little bit of a work in progress. All right, so that's the end of the presentation. And I kind of just wanted to point everybody to this form where if you sign up, we'll notify you when the beta program begins. And, if anybody has any questions, my email is at this address. Thank you.
So just for the purposes of this recording, I'll go over some questions that were asked in the previous iteration of this talk, where we had some technical issues. So Patrick asked, would standalone applications be allowed even in the absence of a network connection? And that the answer to that is yes. So code signing is kind of our licensing solution, and it's all self-contained. It doesn't need to phone home to Wolfram. Dave asks, is the standalone applications program only for commercial applications, or is it also for open source free applications? So we're interested in both scenarios, and that would be something to explore when the beta program goes live. And as a reminder, I put the sign-up form to be notified when that beta program begins in the chat, and it's also in the slides. Armin asks, will it also be possible to develop and compile code using C#? So currently, the only binding we have is in plain C. And however, any users who are interested in making their own bindings can, and we'll be kind of like, we'll see, we'll be aware of what people want. Like if there is a particular binding that people are interested in, make sure to tell us. So Ray asked, what is the size of a standalone Hello World program? So as Todd was saying yesterday, he used his Hello World was like around 200 megabytes, and that the way that he gets to that is right. So we take out MKL and we use a smaller alternative, and then we basically take out literally everything from the layout. All this kind of cool functionality that we have that we don't need for a particular application, goes out the window. And so at that point, it's just like I was saying, it's like stuff like the kernel dynamic library, really core critical stuff. So Dave asked, what form is the cost of using the Wolfram Language Runtime in a standalone application? And as examples of options, like, is it the percent of application sales price? Is it the fixed cost per application? And so Todd, I think, had a good answer to that. He said final numbers have not been determined, and various things will factor in, such as like how much of the language you use. So I think that's all the questions there are. So thanks all.